Okay, let's continue. So in the last class we saw how to build a Flash ADC. The idea is pretty simple. This is the most straightforward ADC you can build. And as we saw, if you want to make an n-bit Flash ADC, how many comparators I'll need? 2 power n minus 1. So you just take the input, compare it with a bunch of reference voltages, and then you get the output. And at the output I'll get 2 power n minus 1 thermometric codes. You kind of sum it up to get the n-bit binary. This is with single-ended. Now with differential implementation, we saw the input we feed like this. The positive input will be the common mode plus half the differential input. The negative was the common mode minus half the differential input. And recollect, the range the differential input can take is from minus VDD to plus VDD, which means we have to quantize the differential input in this range. So in principle, if you had both minus VDD and plus VDD, you can generate these reference voltages directly in a differential fashion. But since we have only from 0 to VDD, we'll have to feed the reference voltage also like this. So the kth reference voltage in the positive, you feed as the same way, the common mode plus the differential kth reference by 2. Similarly, on the negative side, it is the common mode minus the kth reference by 2. And we saw how to generate these positive and negative references. You just need two resistive ladders like this, operated between 0 and VDD. So let us say the bottom one here gives the first positive reference. Now you have a similar structure, and here the top one here gives the first negative reference. It just keeps balancing. You keep going up in one ladder, keep coming down in the other ladder to generate the differential references. And also this is the inputs and reference. So to feed to the comparator, we actually have to do this. Let's make some space here. So you have to subtract the positive input with the positive reference and add the DC bias. That will be the first input to the comparator. The second input will be the negative input minus the negative kth reference added to the common mode. And we saw a bunch of ways to subtract the reference from the input. One straightforward way is to store the reference voltage across a capacitor. So let us say in one phase, you apply the kth positive reference and VCM. So that will store this voltage. And in the other clock phase, you go and feed the input here directly. So here you get the required input. The same thing you do for the negative side also, right? Now a variation of this is, instead of storing the reference across the capacitor, you can also store the input across the capacitor and you feed the reference. So that will give the reference minus the input, which is also fine. And we also saw we can do this reference subtraction not just in voltage like this. You can also add or subtract references in current, right? And also recollect, when we had multiple comparators like this, the clocks reaching the first and the last comparator will definitely have a skew, which means if you locally sample the input in each comparator, since the clock has a skew, the input processed by these guys will be entirely different. And what was the solution for this? Yeah, you have a global sample and hold. You have a common sampling circuit like this, and the signal fed to the comparators, you make sure it is held, so that even if there is any change in the clock edge, since the signal is held like this, it doesn't matter whether you sample at this point or at this point, it's all going to be same. So you sample this and you buffer this and then give it to all the comparators. So you give the reference voltage also, say this is the last reference voltage. This is the first reference voltage. You get the thermometric outputs here. And then you go and add all of these individual bits to get the n bit binary out. And one thing here is, as I mentioned, the Flash ADC is typically used for about 4 or 5 bits of resolution. So the maximum signal to noise ratio you expect is about 30 dB or so. And for that level of linearity, you can have a simple track and hold like this. You don't need to do all complicated business and have a switch capacitor amplifier for this. This buffer can be a simple single transistor voltage controlled voltage source. That will do. So of course I have drawn this for a single ended case. The same will hold good for a differential version also. And then we saw a couple of non-idealities we can have with the comparator. So the first non-ideality we looked at was offset. And the way we deal with offset is as follows. One brute force way to tackle offset is to go and increase the area of the devices. It turns out that reduces the standard deviation of the offset. So to start with, to begin with, you start with a reasonably large dimensions for the transistors. But let's say you want to reduce it further and you can't keep increasing it further. What was the solution to reduce offset? Yeah, calibration, but what else you can do? You can put an amplifier. Again, the idea is only if the input is very small, the comparator's offset will cause an issue. So you make sure the input is amplified first and feed it. So you can have a preamplifier. And so basically this is what you do. You put a preamplifier before the comparator. And if the comparator has an offset of A, after you add the amplifier, what is the overall offset? Right. So now with the preamplifier, we had two considerations. We wanted to keep it a dynamic amplifier so that it doesn't draw any static power. And also this amplifier's offset should be first corrected. And the common way we do this is by calibration. We saw a couple of ways in which you can do this. And in addition to this, if you want to reduce the offset further, you can go and calibrate the latch directly. This is what typically we do. And we also looked at the issue of metastability briefly. So this arises because the comparator is going to regenerate like this with a positively growing exponential. So if the input is small enough, the comparator regeneration time will also be really long. So which means, say this is the time available for you to finish the comparison. At the end of this clock phase, the output might not have reached a valid logic 0 or logic 1. So that's an issue. So again, the issue here is because the input to the comparator is really small. So what is the natural solution? You put an amplifier, so this preamplifier will also go and help you. So this is where we stopped. So finally the Flash ADC's top level picture will look like this. So before the latch, you try to put a preamplifier. So let's see if I can add that here. We'll push this and just put a preamp before this. So we'll have a preamplifier here. So the references will be given to this. And this is then given to the latch settings. Now remember, the reference is now given to the preamplifier, so the reference subtraction should happen here, right? So whatever we saw for the reference subtraction using the capacitors, so this is the input, this is the reference plus and VCM. So this will go at the input of the preamplifier. Okay? So this will be the preamp. Because you subtract the reference, amplify it, and the amplified input you feed to the comparator. So this is how a practical Flash ADC is made. So any questions on this? No question. So which means today if I ask you to go and design a Flash ADC, you should be able to do. You better be, because that will be the first project. So the problem statement will be out.
Components required is very large.
Yes.
The number of bits are.
Yeah, exactly. So that's why I mentioned it's about 4 to 5 bits, not more than that. Okay. Because as he pointed out again, for n-bit flash, you need 2 power n-1 comparators, 2 power n-1 preamplifiers. So if you increase the resolution by 1 bit, what can you say about the number of resources I'll need? That kind of doubles. So you limit it to 5 bits. So that's why in the rest of the course we'll see what all we can do to get a higher resolution ADC. So in that quest we'll come up with new techniques, new architectures and so on. But of course, before abandoning Flash as such and trying for a new architecture, let's see if we can do something better. Let us see if I can increase the resolution of a Flash without actually having to double everything I need. Okay. So that will be the first thing that we'll try to do today. So let's see if we can do that. So again, in a Flash, let us say differentially we are trying to resolve the input in this range. We are comparing the input with so many reference voltages. Okay, I don't know how many I have something. And this is giving an n-bit Flash. Now if I want to make an n plus 1 bit Flash, what can you say about the number of reference voltages I'll need? That will also double. And so which means in addition to the existing reference voltages, I'll have to introduce new reference voltages. And where do you think those reference voltages might lie? So basically between every two, I'll go and introduce a new reference voltage. Clear? So this is clear. So let me actually move to the next page. So let us say this is k plus 1th reference voltage, kth reference voltage, and you have a bunch of them up and down. In between these two, I'll introduce a new reference voltage. And what is the value of that reference voltage? Average of the two, fine. And that is VRK plus 1 plus VRK, fine. So first let me sketch the comparator for these two parts. Okay. So I'll draw a single-ended case first. So I'm feeding the input, the k plus 1th reference. This goes to a preamplifier as we saw. Okay. And the amplified output is fed to, let us say, the strong arm latch. And remember, the output of the strong arm latch, you have to feed it to an SR latch, because the strong arm latch gives output in only one clock phase. You put a latch to hold it for one whole clock period. So here, what is this voltage? I mean, the input is this, gain is this. What is the output? A times the difference. Okay. Fine. So similarly, I'll have an identical copy for the kth reference also. So this is just so if I were to increase the resolution by 1 bit, I also need to compare my input with this reference voltage. So in principle, if I am not smart, I'll just put 1 preampere with Vi. So this is the new reference voltage, average of the two. Give this to a strong arm latch. And then the output is given to the SR latch and you are set. Now if I do this, what is this voltage? What is the output of this preamplifier? Yeah, same thing, A times the input minus the new reference level, which is average of the two existing voltages. Fine. As of now, I have not done anything drastically new. It's the same thing. So now when I do this, I see I'll have to introduce one thing between every two like comparators. So I'm doubling the number of preamplifiers and the comparators. So let us see if we can do something smart. Now one thing is for sure, I need to make a decision as to whether the input is greater than this or less than this. So something that takes some analog input gives a digital output is needed. So this is something, let us say, we can't touch now because something has to give me a digital bit. So this looks like something that's non-negotiable. So let's see if we can get rid of this fellow. So at least let's see if I can reduce the number of preamplifiers. So if I don't need to have this, which means I need to generate this voltage from what I already have existing. And is there a way to generate this voltage from the existing voltages? Yeah, in English, what do you have to do? If I take the average of these two, you get this. So that is in English. If you translate that English solution in circuits, how do you take average? You put a resistive divider. Now if I do this, I don't need to have an additional preamplifier here. So at least the number of preamplifiers I need reduces by a factor of 2. So this technique is called interpolation, and in particular this is called 2x interpolation for obvious reasons. I mean, basically in a flash, if you increase the resolution, number of preamplifier doubles, number of comparators double. You want to reduce the increase in the resources. That's all. So this is 2x. So now of course I don't necessarily have to stop at 2. Let us say I want to do a 4x interpolation. If I want to do 4x interpolation, now we can think of it like a recursion. In between these two, I'll add one new branch. So I'll have one strong arm latch to make one comparator. So I'll actually erase this thing now. I'll also not need this. Oops. Similarly, in between these two, I'll have one additional set of comparator. And how will I get the input for this fellow now? I'll have to average these two now. So this will again split into two equal resistors, right? Is that clear? So now again I have to average these two. So you split that one single resistor as two resistors again. Similarly at the bottom side you do the same thing. So I mean this you can keep doing this. Now of course we have seen only for single-ended. Let's look at a differential case because for a 2x interpolation, differential implementation is slightly more simpler. So what I'll do, I'll take here. So the idea is clear. The goal is to try to reduce the number of resources I'll need in a Flash ADC. Here I am at least trying to make sure I don't need to have preamplifier in each path. Okay, that's the idea. So let's try to replicate the same idea for a differential implementation. So in a differential case, remember I will feed the inputs in a differential way. So Vi plus minus say the k plus 1th reference plus a common mode. Similarly on the bottom side it is the negative reference voltage for the k plus 1 plus VCM. Okay. So this is the input to the preamplifier, and output of the preamplifier I am giving to the same thing. Okay. So if I just look at the differential input here, so that is going to be differential input minus the differential k plus 1th reference. Okay. Individually I will feed it like this, but the difference is this. So which means what can you say about the differential output here? A times that. Now recollect, whenever I had a differential input, the positive input was given as the common mode plus half the differential input. The negative side, it was common mode minus half the differential input. Now this is the differential signal I have. So what do you think might be the positive output and negative output individually? If I had a differential signal, typically on the positive side I have plus half plus VCM. The negative side I have minus half that differential signal plus VCM. So here this is the differential signal. So what will be the top side? I mean basically plus half of this added to a common mode. Same way in the negative. So let me actually write that also. So let us say here, I need some space. So this is A times, or I'll write it, the common mode plus half of this differential output. Fine. Similarly at the bottom side I'll have this. So I'll not write the bottom one, okay? Or maybe I can write it. I'll erase this and write the bottom one. This is VCM minus half of this. This is fine. I'm just splitting the differential component. Half of it comes here, negative half comes here with some DC bias at the output. So I'll have the same thing for the kth branch also. So I'll just replace everything by k. This is what I'll have. Let's see if I can make some more space. Okay. Now again I want to do 2x interpolation. Okay. So I'll remove all this to avoid clutter. This is the input I feed here. Okay. So I want to add a second path here. When I interpolate, I don't want to have a preamplifier, right? I just want to have the comparator directly and get this done with. So which means what should be the differential input that goes to the comparator here, ideally? No, I mean, let's say you have a preamplifier here and do this, right? Then ideally, what do you expect the differential output to be? A times? Just the differential. See, if I take the difference between the two, what do I get? A times the differential input minus the k plus 1th reference. So here what will I get? A times? Yeah, average of the two reference voltages, VRDK. That's all. Differentially, this is what I should be applying here. But I am saying I am very stubborn and saying I don't want to have a preamplifier here. So which means somehow I need to feed two signals here so that the difference looks like this. So can you stare at the circuit and tell me if we can do some arrangement here? Can you see clearly? I mean, the only thing I want is the difference should look like this. Is there any two voltages whose difference is equal to this? Huh? Positive of the top and negative of the bottom. So hopefully you understand. If I take positive from the top, that is going to give me half of VID minus VRDK plus 1 by 2. This I get. Similarly, I give the negative and feed it here. That will get inverted. So I'll have VID by 2, so that gives me A times VID. Similarly, this gets inverted. I have minus VRDK by 2. This is exactly what I need. Clear? So that's what we'll do. We'll do something like this. And voila, you don't need to put the resistors here. can actually get this 2x interpolation for free. Yeah, exactly. I mean, either you can take the positive from here, negative from here, or you take the negative from here, positive from here. I mean, the decision might be flipped that you have to take it. That's all. So this is again a 2x interpolation, and it's pretty simple when you do it in a differential implementation like this. So yeah, so this is one nice thing about interpolation. When I do this, I see that the number of preamplifiers I need doesn't necessarily increase, and that is particularly a good news because if I look at the top level implementation of a flash, what I am claiming is now the number of comparators is more, but the number of preamplifiers is lesser. And you see all the preamplifiers are connected to this buffer. So, and which means if I have lesser number of preamplifiers, the capacitance offered by all the preamplifiers is going to be smaller. So the load that the buffer has to drive is going to be small. So that is the good news. So that is the one thing nice about this. But what do you think might be the limitation of this? Because looks like I can keep doing this forever, right? I keep putting 1000 resistors, I can get anything. Well, let's say we can design something. It's not a problem. Sorry? Noise because of resistor will not be that critical. Let us say because again flash resolution is small, so it's not that critical. I mean, what do you think might be something that, I mean, resistor area is not so much, let us say. No, right? I mean, you are not, power you always look from VDD to ground. This is basically between these two, not so much critically. See, this entire premise is based on the assumption that you get this voltage here and this voltage here. Now, of course, input voltage is same for both the comparators, both the preamplifiers here, fine. These reference voltage you might have generated, that is also fine. But what is one thing that can change? Yeah, gain, right? I assume that the gain for the two preamplifiers are same. That is something you cannot guarantee, right? So that is the thing that will limit in practice. And I mean, in a more, fundamentally, this entire thing makes an assumption that you will be using a preamplifier in your circuit. I mean, it can so happen that in your case, you don't need a preamplifier. Then this might not buy you anything. So that is the limitation. So that's why typically this is not commonly done in practice. But what is commonly done is a different kind of interpolation. Let's look at that. But till this point, the idea is clear. So one of the main limitations is the preamplifier's gain should be matched, and also the mere fact that you need to use a preamplifier. Otherwise, this is not any good. So let's see what is the recent trend now and how interpolation is done in a different way. So again, let me take a differential case, and let's even consider I don't have a preamplifier. I directly feed the differential inputs to the strong arm latch ADC, and the output of this fellow is given to the SR latch finally to hold the output. And let us say this is the K plus 1. This is the K plus 1th branch, the K plus 1th comparator. Similarly, I'll have identical structure here. Let us say this is QK and QK bar. Right? So again, let me draw this here. This is the differential reference for the K plus 1th level, differential reference for the kth level. Now if I interpolate this by a factor of 2, I'll introduce an additional reference voltage here. That is going to be the average of the two. So I'll simply call it as K plus 0.5. Right? Just for notational simplicity, I'll do this. So again, now the idea is I have to make a decision on whether my input is greater than this or less than this based on these two guys, right? Now let's take some cases. Let us say the input is lying somewhere here. This is my input. So it is smaller than both the reference voltages. So then what can you say about output of both comparators? Its input is smaller than both the reference voltages. Both these guys are 0. If both these guys are 0, what should be the output of this comparison? 0. So when the input is lying here, no issues. Similarly, let us say the input is lying here. It is greater than both the reference voltages. So both of them will be 1. If both of them are 1, this is also 1. No confusion if the input is actually beyond this and this. When is the problematic situation? When the input is lying in between, right? So let's only focus on that case now. So the tricky part comes when the input is somewhere here, because here is when we have to decide if the input is in this range or in this range. That is the additional bit of information we need when I compare the input with this. Now let us say for any input that is lying in this range, what can you say about the output of the bottom comparator? If the input is lying anywhere in this range, what will be the output of this comparator? 1. The input is greater than that, so this will be 1. So I will say Qk goes to 1. I mean, the input is lying somewhere here. Anywhere if the input is lying, it is definitely greater than this reference voltage. So the output of this comparator will be definitely 1. I mean, this comparator is checking if my input is greater than this reference or not. If my input is anywhere in this range, it is definitely greater than that. Similarly, what can you say about the output of this comparator? 0. Let's say this is 0. So this is 0 and this is 1. Fine. So this much is clear. Now let us say the input is lying somewhere here. If the input is lying here, what should be the output of the additional comparison? 0. So here this should be 0. Okay. Now let us say I sketch the outputs of the two comparators. Okay. So let us say the top one, as I see, goes to 0. The complement goes to 1. So if I sketch this, remember initially this is the output of strong arm latch. Initially the outputs are reset to what voltage? Initially both outputs are reset to VDD, and then one of them goes to 0. So here the Q goes to 0, the Q bar goes to 1. Fine. Let's say this is the time axis. This is 0. I'm just drawing time axis down for simplicity. Now let us say, let me make some space here. Now if I try to draw the outputs of the bottom comparator, so that will also be doing something like this. It will start from VDD, one of them goes to 1, other goes to 0. But if I try to sketch both of them on the same graph, will there be any difference between the two, or both of them will look very similar? I mean, identical, or will there be any difference at all? I mean, if you say it's going to be almost same, what you mean is that if I sketch the output of the second comparator, that will also do something like this, which means both of them are finishing the comparison at the same time. So look at the case, the input is lying somewhere here. Do you think both comparators will finish comparing at the same time, or one will take longer? Remember, if the input to the comparator is small, it is going to take longer. So this is the input to the bottom comparator. This is the input to the top comparator. Tell me which one will finish faster? Bottom or top? The input to the top one is very large, so that's going to be faster. So if I sketch the output of the bottom comparator, So that is going to take longer time, right? So it will basically do this same thing, but it's going to take longer. So this is QK. Okay. Now if I keep increasing the input slowly, if the input starts to increase, what can you say about the delay of the bottom comparator? That is going to be smaller. For the top one, it is going to increase, right? Until what point, I mean, I'm increasing the input. Till what point do you think the top comparator will respond faster? Till I reach here, the top one will be faster, bottom one will be slower, and the moment I cross here, the situation reverses. So this is one difference we can see when the input is lying here or here, right? So I'll write this out. So if the input is lying in this range, I find that the top comparator is finishing faster. So I'll basically write it like this: Qk plus 1 goes to 0 before Qk bar goes to 0. I mean, that is a different way of saying the top one is finishing faster than the bottom one. I mean, or the other thing is also right, which means Qk plus 1 bar goes to 1 before Qk goes to 1. So this is true if the input is in this range, and if the input is in this range, the additional result should be, what should be the output of this comparison? If the input is in this range, 0. Fine. Now if the, as we saw, if the input comes in this range, so input is lying somewhere here, the bottom one will finish faster than the top one, right? So that is the difference. So let me write that also. So what we are saying is, now my input is lying somewhere here. Now the bottom one will finish faster than the top one. And what can you say about the output of this comparison now? If the input is in this range, comparison with this one should give you 1. So the statement, I'll just reverse it. Now it is now Qk bar goes to 0 before Qk plus 1, or I can say Qk goes to 1 again. I have just rewritten the fact that in this range the top comparator will finish faster, in this range the bottom comparator will finish faster. That's all. So let me actually copy paste the statements we made. So this is the first case, this is the second case. Fine. So now you see, to get this additional bit of information, all I have to do is what? What should I check for? Huh? Yeah, now the thing is, if I were to make this decision, I will see which of the two comparators is finishing its job first. That is saying, I will check whether this goes to 0 first, or this goes to 0 first, or the other one. Okay. So now you see, the problem reduces to a simple digital electronics problem. You are going to see which of the two signals is going to logic 0 first, right? So that is the solution in English. Now we'll try to get a solution in circuits, and this is a digital electronics. So to solve this, you first draw the truth table. And why do you draw truth table? Because truth table never lies. Okay. So I'll write that Qk bar, Qk plus 1, and then I want to make decision on Q. Okay. So again, I'll slightly be more hand wavy. So the first condition says Qk plus 1 goes to 0 before Qk bar, right? So I'm not going to be very strict in this. All that means is, when Qk plus 1 goes to 0, the other signal is close to logic 1, right? So I will say, when Qk plus 1 goes to 0 like this is the situation. This is going to 0, but loosely the other signal is close to logic 1. When this happens, Q out to 0. Now we'll have the opposite like this in Q square. Fine. Now remember, I am considering these two signals Qk plus 1 and Qk bar, and eventually both of them go to 0, right? And when they go to 0, what should I do to the output? So remember, let's look at this, waveforms. The moment I find Qk plus 1 goes to 0 first, I've made my output 0. But after some time, this guy also goes to 0. At that point, do I change the output or no? I don't change. Same thing here also. I didn't draw this waveform here, but yeah, you get the point, right? So here also I should not change, so I'll have to hold this. So now look at this. You might have taken digital electronics fresh because I took 10-12 years back. So if I look at this, if you look at this, does it remind you of something? 0, 0 is a whole state, and that is basically, it's an SR latch. Okay, it's an SR latch. So should it be a NOR-based SR latch or a NAND-based SR latch? If it's NAND-based SR latch, if my inputs are 0, 0, what will happen to the outputs? It's a NAND gate. One of the inputs is 0. What will happen to the output? It is not holding it, it is flipping it. So this should be NOR-based. Okay. So that's all I have to do. I will feed Qk bar to this, Qk plus 1 to this, give it to a NOR-based SR latch, and one of them will give you Q out. I think this is Q out. I don't know if this is Q out, you can work out, but you get the idea. So the solution is now pretty simple. All I have to do is the following. Let me copy paste this. So in between every two comparators I have, I go and put an SR latch like this. This should be a NOR-based SR latch. Okay, and I should be comparing Qk bar and Qk plus 1, okay, or the other two. So this is going to be, let me erase this, Qk plus 1 and Qk. So this will give you the additional bit of information and you are set. So in between every two sets of comparators, you go and put this NOR latch and you get a bit of information for free. So here also we are doing this 2x interpolation, but we are not using the information in voltage, right? What are we checking here? No, it's not even binary. In English, what were we checking? Yeah, we are checking which of the comparators is finishing decision first in time. Okay, so we call this time-based interpolation.
So before t equal to 0, Qk bar and Qk plus 1, both are at logic level high.
Yeah.
So what is the
Yeah, then what will happen? So if both of them are 1, this will become 0, right? If both of them are 1, this is going to be 0. And remember, even the strong arm latch is going to give the output here. During this phase, you don't get any information, right? So, what is this? Yeah. When the strong arm latches are reset, both of them are 1. At this point, this will be 0. But after the decision is made, you get the data. Right? Okay. So again, this idea is not that thing, right? This is the same thing we do in cricket also. Right? If you, let's say it's IPL or some ICC tournament, you find two teams have the same points, they won the same number of games, lost the same number of games. How do they decide which team is in the top? What is net run rate? It is just saying which team, if a team finishes faster, if the margin of defeat is larger or margin of victory is larger, the team goes. So there also they do the same thing. I mean, it's all, like if you are an engineer, you try to, like understand solution, try to adopt everywhere. So yeah, I'll just quickly show some things in the literature. So this is probably one of the early papers where this idea was first adopted, and this is from Inshang Shu from MediaTek Taiwan. So here they try to make a 6-bit ADC. So in this 5 bits is from Flash, and 1 bit you get from this time interpolation. Okay. So I'll just not look at this alone. Yeah. So as we saw, between every 2 comparators, you go and put this NOR-based SR latch, and that gives the output. And the other interesting thing to note is the comparator architecture itself. So here, if you look at this, focus on this part. What does it remind you of? Assume that this is basically connected to something like this. I have a differential pair like this, cross coupled CMOS inverter. This is essentially your strong arm latch. Okay. So in addition to this, they seem to have added some things here, and the reason we can look here. So the effective equivalent of this is basically this. So what they have done, they have added some resistance at the source, and if you recollect, in the last class I briefly mentioned that you know that you are going to have offset in your latch. If you intentionally go and introduce an offset, you can approximately make the offset equal to the reference voltage needed in the flash. So this way the comparator will compare the input with this reference voltage automatically. Okay. And that's exactly what they have done here. They are introducing resistors on either sides, change the value of the resistors appropriately so that the reference voltage is inbuilt as offset in each comparators. Yeah, that's what comparator built-in offset, and that they are doing it by introducing an imbalance here. So here, let us say this is 5 bits, they have, let us say 31 comparators. So we have so many of them. So in each of the comparators, you go and change the value of the resistors so that in the first comparator, the offset is equal to the first reference voltage. Second comparator, you change the resistors so that the offset is equal to second reference voltage, and so on. And again, the idea is when you do this, there is no need to generate the reference voltages using resistive ladders, because you have kind of introduced that reference as an offset here. And again, this is pretty old. This is in 2013 or so. Yeah. Good. So now we saw how to do this interpolation in time. This is 2x interpolation. Now we can also naturally extend it to 4x interpolation, and the extension is also simple. So let us say if I look at the input versus the time taken by the comparators. Let us say this is the kth reference voltage, k plus 1th reference voltage. So let me show here. Yeah. If I keep increasing the input, the delay of bottom comparator, is it increasing or reducing? That is reducing if I keep increasing. Similarly, the top comparator's delay, that will increase, right? So if I sketch this, the bottom comparator's delay starts to increase, and the top one will start to increase like this. And exactly at the middle reference voltage, the delays will be equal. That's what we kind of exploited, right? Now this was giving you a 2x interpolation. Here we just checked if the time taken by the top comparator versus the bottom comparator is greater than 0 or less than 0, right? Now let us say you want to do 4x interpolation, which means we have to compare with these voltages. Let us say this is k plus 0.25, this is k plus 0.75. Now what this means, I have to check if the time delay is this much or this much. Again, both should be equal. It's not drawn it nicely. So now what I have to do is, if I want to extend it by 4x, I should not be just checking if one comparator is finishing earlier than the other. We should be checking if one comparator finishes delta t before the other. That's what this means, right? When I had this middle reference, it just checked if one comparator finished before the other. But here, to make the decision, I have to see if the time delay is less than delta t or greater than delta t. So I have to compare with minus delta t, or say it's less than minus delta t. Similarly, on the other side, it is greater than plus delta t. This is what you have to do in principle. So this is again the solution in English. If you translate it to circuits, you can get actually couple of different variations. So I'll just show a couple of them and we'll wrap today. Yes. In the previous one, one extra bit. Yeah, correct. No, you think about it. Let us say you have 1, 2, 3, 3 comparators, 2-bit flash. So you sum up these 3, you get a 2-bit data. Now what I am doing, I am introducing this here. So in principle, you can also do this, and then you get, now you get a 3-bit, right? You add everything. So now for 2-bit extra, you have to do this. You have to check if the delay is greater than delta t, less than delta t, greater than minus delta t, less than minus delta t. And one way this is done is this. Again, this is not very new. This is again 2015 from Asian Solid State Circuits Conference. And the previous one was from VLSI Symposium. I don't know if it's given. Yeah. Anyways, and VLSI Symposium and anything in Solid State Circuit Society is the top place where state-of-the-art works are reported. So here they have done a 4x interpolation. 4x means they get 2 bits of additional information. So total is 6 bits. So they have a 4-bit flash plus 2 bits of this. Yeah, as they see, yeah, they say, right, number of comparators for a 6-bit flash you need 63, but they are using only 4 bits, so it reduces to 16. Let's just look at this and stop. Yeah, so yeah, here they kind of refresh the voltage domain 2x interpolation. This is what we saw in the beginning, where you kind of eliminate the preamplifier required. The second one is the time interpolation, where you get rid of the strong arm latch and have an SR latch. So this is 2x. Now for 4x, yeah, the same thing we saw. 4x, you have to also do this. So what they do is the following. So in between every 2 comparators, now you introduce 3 latches. The first latch is as usual, it checks if the delay is greater than 0 or less than 0. Now the bottom one will check if this is less than minus delta t or greater than minus delta t. The top one will check if it is greater than plus delta t. And the way the latch checks if the delay is greater than delta t or minus delta t is as follows. So recollect, we saw for the comparator, we told we can intentionally introduce an imbalance in the 2 differential halves to make the offset equal to a reference voltage. Now you take an SR latch, that is also a differential case with cross coupling. Now if both the NOR gates are identical, this will compare if T1 minus T2 is greater than 0. That's what we used. Now what you do, you want to compare if it's greater than delta T. So what can you do? Yeah, you kind of create an imbalance in the 2 NOR gates. That is again introducing an offset in the system so that the signal is not getting compared with 0 but to some other value. So the same thing they do here. Yeah, so this is basically your cross coupled NOR gate, or this is NAND gate. Yeah, I think they use NAND based SR, anything is fine. So here what they do is this, I think the ones in gray have a smaller size than the ones in black. See, nominally these two should be identical, these two should be identical, but they intentionally make, I think, sizes of this one smaller or larger to create that imbalance. Same with PMOS. So this again one clever way of kind of using bug in your circuit, make it as a feature, right? So this is one line of thought. Again, the solution in English is this: I have to make sure I compare my time information with minus delta t and plus delta t, right? So there is another way in which you can translate the same thing in circuits, and it turns out there is a class of circuits called time to digital converters, or called TDCs, that exactly do this. They check if time is greater than whatever you want, right? It basically checks if the falling edge or the rising edge of two signals is greater than or less than a particular delta. I mean, I'm not going to how to make TDCs because that is a separate course. So some of you might have taken, or others you can look at E698G lectures by Professor Chitra. So you can use a TDC for this, and that also people do that. So we can show this here. So this, yeah, slightly recent, 3 years back, 2021, in the Journal of Solid State Circuits. So here they are doing 8x interpolation. So which means how many extra bits of information they are getting? 3 bits of extra information from time. Okay. So this is totally what, 6 bits. So probably 3-bit flash plus 3-bit in time. Okay. And let's just look at that. Yeah, they do the same thing in between every 2 comparators. You take the, let us say, the negative of top, positive of the bottom, or vice versa. Take the positive of top, negative of the bottom, and give it to a time to digital converter. Now a simple SR latch we saw can be thought of as a 1-bit TDC that checks if the T1 minus T2 is greater than 0. Right? Now we can make better TDCs, and that's what they do. And is there something interesting? Nothing major. Okay, let's look at the comparator architecture. So again, this is the voltage comparator. What is this? This is a strong arm latch. So in addition, they have all the circuits. And why are they doing this? Yeah, again, to intentionally create an imbalance, to make sure an offset is induced, and try to keep this offset, yeah, almost approximately equal to your reference voltage. So yeah, maybe we'll just look at the spectrum and let's do a spectrum calculation so that you guys still are comfortable. So this is the final output spectrum they have. So yeah, they're plotting 4096 point DFT. So this is 4096. Okay. Signal is lying on this bin. So maybe, I don't know, this is 1900 or something. Again, remember, how do you choose Fin by Fs to be? And how should M and N be? Co-prime, right? So this might not be exactly 1900, could be 1901 or something. So probably Fin is 1901 by 4096 times Fs. I don't know, I'm just guessing, but let us say for simplicity it's 1900 for easy calculations. So if the input is lying on 1900 bin, where will the third harmonic lie? 1900 times 3, 19 tables. What is that? 5700. So of course, will this be within the thing or no? Yeah, N is 4096. So maximum I can have is 0 to half 2048. You can see 2, this is 2048. Yeah, so where will this alias to? I mean, this is basically minus 4096 can put 10 in the mind, 16 fingers, blah blah blah. What do you get? Yeah, something. And that's roughly you get here, right? 1600 or so. So I just subtracting these. It's okay. So again, please make sure you are comfortable and fluent with these things, because finally any analog or mixed signal circuit you will characterize in frequency domain. If you don't know where each tone is coming, you'll have no idea as to what's happening in the circuit, whether it's a real problem or a fabricated problem due to, like improper FFT and stuff.
So where is the second one?
It's not there here. And typically, right, I mean, you have taken E613, if you have a fully differential circuit, second harmonics cancel. Okay? So maybe I'll just, couple of minutes, I'll just mention one thing. I didn't expect it to take so much time. But anyways, there is one other technique I'll just briefly mention and we'll wrap, called folding. The idea is the most simplest you can think of. So let us say I look at an ADC characteristic. So it's going to look like this in the positive side. Negative side also it will be exactly symmetric. Fine. I don't know if it's symmetric, but it should be symmetric. Huh? Now let us say I make an ADC that compares my input only with positive references. Okay. My input can go, differential input can go negative and positive, but let us say I have made an ADC that compares only with positive reference. Now if the input is greater than 0, there is no issues, I will feed this directly. If the input is less than 0, can I use the same ADC to make the decision? Huh? Remember, the characteristic is exactly symmetric. So instead of applying Vi, if I apply minus Vi, we are set. Right? So basically, what we are doing is the following. This is the input, but the input you are feeding to the ADC is like this. If it's positive, you feed it directly. This is V in ADC. If the input is negative, what you are doing? Huh? If the input is negative, we are inverting it, so it becomes positive. I mean, minus into minus is plus. Okay? So that also becomes like this. So this is why it's called folding. So the if you again draw the full picture, it looks like this. First thing is you feed the input and check if it is positive or negative by doing a 1-bit comparison. Okay, and if let us say this is D, if the signal is positive, you feed the input directly like this. If the sign is, if the input is less than 0, this will be 0. You should flip and connect it. I mean, instead of feeding plus Vi, here it should be minus Vi, and that you can simply do by crisscrossing it like this. You give the negative to the positive, positive to the negative. So you just need to have a switch like this. This will be clocked with rebar. So if let us say this is giving you some n-bit data, you take the n bits like this, and remember D is the sign bit, you put it in MSB utilities. Again, these are all relatively old techniques. So just like this is basically we call as 2x folding. You can obviously extend to 4x, 8x and so on. Basically if you want to do, in 2x we did this, for 4x you kind of do this and stuff. And just like how we do interpolation in time domain, you can also do folding in time domain. You can think of all crazy ways. Anything and everything is possible, but I'll not go there. So I'll stop here.